The broadcast is now starting. All attendees are in listen-only mode.
Good morning. This is Neil Polhemus. I'd like to welcome you to today's webinar, which is titled 2018's Top 10 Ways to Visualize Your Data. Since it's the end of the year and everybody's doing their top 10, I thought I'd use this webinar to show you some of the graphs that have been most effective, for me at least, over the last year in visualizing different aspects of my data. Now, the way the webinar is going to work is we will examine 10 of the most useful graphs for data visualization. Graphs that were popular in 2018 because they did a good job of pulling and displaying the information in a particular data set. Now, we're going to do it in the context of selected data sets. Now, I've gotten together a total of 8 data sets, some of my favorite data sets. And what we're going to do is we're going to look first at the data and then talk about the graphs that seem to be most effective in displaying the information in that data. Some of the graphs will be fairly specialized. It does sometimes require a special form of graph to really get out the information in a particular data set. But I think you'll see that as we go along. Now, I must admit, the list is subjective. They are my choices, ones that I've picked, and they're in no particular order. And I haven't tried to rank them from 1 to 10 or anything like that. I've just picked out 10 useful graphs. And finally, I will mention before we get started that I've concentrated in selecting the graphs in this list on descriptive graphs. Not graphs that typically follow up a particular analysis. I mean, they're very useful graphs, for example, biplots in a principal components analysis and that sort of thing. That's not what I'm going to concentrate on today. I'm going to concentrate on graphs that basically stand on their own as good illustrations of what's important in particular data sets. Now, the first data set we're going to look at is one of my favorites. It has to do with eruptions of the Old Faithful Geyser in Yellowstone National Park. The Old Faithful Geyser is one of the most visited what should I call it? Tourist areas. Anyway, a lot of people go to Yellowstone National Park to look at Old Faithful. I have a data set here with a total of 272 rows in it. It's the duration in minutes of 272 consecutive eruptions of the Old Faithful Geyser. So, for example, the first eruption in the data set lasted 3.6 minutes, the second lasted 1.8 minutes, and so forth. We also know for each eruption the waiting time until the next eruption. So after watching a eruption that lasted 3.6 minutes, we then had to wait another 79 minutes until Old Faithful erupted again. Now, with this particular data set, there are a number of questions that would be interesting. First off, it's interesting to ask, what is the distribution of the duration of those eruptions? Secondly, what is the distribution of the waiting time between eruptions? And finally, an interesting question might be, is there a relationship between duration and waiting time? Now, the first graph I've selected, we'll call this graph number 1, is something called a violin plot. A violin plot is an enhanced version of a box and whisker plot. You're probably all familiar with the box and whisker plot. It consists of a box covering the center 50% of a data set with whiskers to the smallest and largest observations. So what you see along the x-axis here is the duration of the eruptions. There were eruptions lasting as short as a minute and a half, and some lasting in excess of 5 minutes. You can see that the median eruption was just around 4 minutes, and the mean here at about 3.5. Well, the box and whisker plot is quite useful in illustrating certain aspects of a set of data, but it misses a lot of the important information about the Old Faithful eruptions. So what we've done with the Violin Plot is we've added above and below the box a non-parametric estimate of the probability density function over that range of duration. Basically, a non-parametric density function takes an interval of a particular width, moves it along the x-axis, and creates a weighted average, a weighted count, actually, of the number of data values within a particular interval. Now, I'm going to switch over here for a moment to actually Statgraphics, where you can see the statlet that we use to create a violin plot, because there is a slider bar here which changes the interval width of the non-parametric estimator. If I widen the interval, I get less detail, and if I reduce the interval, considerably more detail. Well, what you can see from the violin plot that you just couldn't see from the box and whisker plot is that the distribution of eruptions is very bimodal. You have a lot of eruptions lasting about 2 minutes, many lasting about 4.5 minutes, but very few lasting in the interval around 3 minutes. A very bimodal distribution. The violin plot is just an excellent plot for showing that aspect of the data, something that you simply could not see from the box and whisker plot. So we'll call that plot number 1. Plot number 2 of the top 10 is also a plot I'm going to show with this particular data set. It's called the bivariate density plot. A bivariate density plot is similar to the violin plot in the sense that it creates a non-parametric estimate of a density function. In this case, though, it's a bivariate density function. You see along the axes here the duration of the eruptions, and then along the second axis here the waiting time until the next eruption. And one thing you can see is that in the space of duration and waiting time, it's definitely a bimodal distribution. You see short eruptions down here around 2 minutes in duration, for which the waiting time until the next eruption tends to be less than an hour, less than 60 minutes. On the other hand, you see a lot of eruptions also lasting about 4.5 minutes, but after those eruptions, you typically have to wait about 90 minutes until the next. Now, incidentally, there's a slider bar here, and by changing the interval width, I can get more or less detail also with respect to the bivariate density function. Well, that's what it looks like as a surface plot. If I click this little checkbox here, we can turn it into a contour plot instead. And if we like, even display the points in the data set. And you can see that in the space of duration and waiting time, which are clearly highly correlated, there are basically 2 groups of observations in that particular data set. Okay, well, back to my slides. Graph number 1, as I said, will be the violin plot. Graph number 2 of the top 10, the bivariate density plot. Okay, now the second data set I'd like to look at has to do with population, in particular the population of the United States. on December 15th, when I put together this talk, the population of the United States was somewhat in excess of 329 million people. That's a large number, but not nearly as large as the 7.5 billion people, of course, around the world. Now, from our Census Bureau, from their website, I pulled a data set that describes how the U.S. population has changed since 1950. The data consists of yearly counts of males and females in various age categories. For example, I know back in 1950 how many males and females were aged between 0 and 4 years, between 5 and 9 years, 10 to 14 years, all the way up to 85 plus. The sorts of questions that are interesting to ask with respect to the U.S. population are, well, I put down 3 that I thought were interesting. How is the U.S. population distributed by age? How does the distribution of men compare to that of women? And thirdly, how has the distribution changed in recent years? Now, there's a particular graph that's very effective in showing population distributions. It's called the population pyramid. The population pyramid is a bar chart that shows for each of those age categories, 0 to 4, 5 to 9, 10 to 14, all the way up to 85 plus, how many males there are in the population and how many females. You're looking here at the data for 2012, and you can see that basically back in 2012, there's a fairly uniform population up to about 60 years old, after which the counts fall off. Now, the way we've implemented this in Statgraphics is we've actually added some animation. So I'm going to go ahead now, go back to Statgraphics and open up a Statfolio that I put together showing the population pyramid. It's dynamic, though. I can, with this slider bar here, change the year for which the population is being displayed. So let me start by sliding it all the way back to 1950. This is what the population looked like of the United States in 1950. Back then, which was 5 years after World War II, the largest population category was children aged 0 to 4. Okay, this was what is called in the U.S. the baby boom. A lot of the soldiers and sailors and airmen, when they came back from World War II, decided it was time to have a family. And you can see lots and lots and lots of babies and very small children at that point in the U.S. population. Okay? You can also see as you go up the table here that by the time you got to 85 and over, there were very, very few people in the population back in 1950 of that particular age. Now, I'm going to add a little animation to this and let the year change. So we'll cycle from one year to the next, and you can watch the changes in the population. Number of things you see. First off, I'll do that again. You see the baby boomers getting older. Right? You see the peak, the largest bar, move up the chart. You see the distribution of the population over age categories leveling off, becoming much more uniform. And you'll also notice a large increase in the number of people 85 and above. There are, or were in 2012, which is the last year that I have data for, almost 4 million females and about 2 million males aged 85 or more in the U.S. population. adding a little animation to the population pyramid definitely is a good way to see changes. And that's why I've nominated population pyramid to be graph number 3 of my top 10. Okay. The third data set I'd like to look at is another one that's of particular interest. It has to do with wind speeds and wind direction at Midway Airport in Chicago. Now, Chicago is called the Windy City, so when I decided to go look for some wind, it seemed appropriate to pull data from one of the airports at Chicago. The data show me for every day and every hour of 2018, the wind speed and wind direction at Midway Airport. Okay, so it starts a little bit after midnight on January 1st and goes through, I believe it's approximately December 15th. Very interesting data set. Now, what sorts of questions might one want to ask? Well, first off, why is it important to even study wind speed and direction? Well, it's quite important, obviously, if you're designing an airport and you want to lay out the runways to know something about wind speed and direction. It's also important if you're creating wind turbines and that sort of thing. It's actually quite a number of applications where people like to study wind. Incidentally, this data comes from the Midwestern Regional Climate Center. It's online. All the data sets I'm looking at, incidentally, today, I downloaded from various sites around the internet. Now, the sorts of questions we might like to ask of this particular data. First off, what's the dominant wind direction at Midway Airport? Okay, is it from the north, the south, the east, the west? What is the dominant wind direction? That would be important, obviously, if you're laying out runways. Be interesting also to know what the average and maximum wind speed was throughout 2018. And also another interesting question is how do direction and wind speed change throughout the day and throughout the year? Now, there's a special graph that's particularly well suited to display wind speed and wind direction. It's something called a windrose. Okay, and graph number 4 of my top 10 is going to be the windrose. What the windrose does is it basically divides the compass up into a certain number of intervals. The windrose I'm displaying here divides the compass into, I believe it's 16 sections. For each section, any particular range of degrees, a petal is drawn showing how many hours during 2018 the wind was coming from a particular direction. Okay, now this happens to be a windrose for 23:53, 7 minutes before midnight. So we've looked at all the days in 2018 and tabulated the direction from which the wind was coming 7 minutes before midnight. Now you can see that the most frequent directions that the wind was coming from at Midway was from the south-southwest. That was fairly frequent, and also sometimes from the northwest. Rarely was it coming from the east, at least during 2018. There's also something called the resultant vector, which is a weighted average of the direction from which the wind was coming. Slightly before midnight, that weighted average in this case was pretty much due west, from the west, You can also see of the 348 observations, the average wind speed was 8.3 miles per hour. Okay, well, that's a static picture. I'm now going to go over to Statgraphics and add some animation to that to show you how things change. So let me pull up a stat folio called Wind at Midway. And the first wind rose I'm going to look at here will be one which shows how it changes throughout the day. This is the picture I showed you before, the wind slightly before midnight. I can use this slider, however, to go back and change the time of day. So I'll slide it all the way back to approximately 1 a.m. And you can see at 1 a.m., again, the predominant direction was from the west, although you see that on occasion it did come from the northeast. Now let's let it run hour to hour through the 24 hours of the day. And you'll see that basically it starts out from the west. Let me just step it myself. As the night goes on, it starts moving a little bit more to the north. By the time we get to 3 o'clock in the afternoon, it's actually moved a little bit past north, and it goes all the way over to the northeast at about 4, that's closer to 5 o'clock in the afternoon, stays there for a little while, and then comes back. So it's very interesting. At least in 2018, the wind tended to shift more toward the northeast in the afternoon, whereas the rest of the day, the dominant direction was the west. Okay. Now, I can also ask how it changed over the year. Here I'm going to use the month operator in Statgraphics to extract data for each month. This is a wind rose for all hours of the day in January. And you can see in January, rarely did the wind come from the east. It always came from either the northwest or the southwest, sometimes directly from the south. Now let me walk it through the months of the year. That's January. In February, it was fairly similar. March, for whatever reason, it shifts dramatically over to the northeast. Okay, stays there pretty much in April, May, June, July. Then in August, shifts around to the south. In September, back to the east. October, November, December, back to the west. Now, that is jumping around a lot, and that's because I suspect the only data I had was from 2018. I suspect if I could get similar data for maybe a 30-year period, you wouldn't see quite as much jumping around from month to month. Very interesting graph. Very well suited for looking at something that has a spatial component to it, a directional component to it. So the fourth graph of my top 10 will be the wind rose. All right. Now, the fourth data set I want to look at is one that I've talked about in previous webinars. It's data from the World Bank. It describes about 170 countries throughout the world. We know, for example, in Aruba in 1961, what the population was, what percent of the population lived in rural areas, what percent of the population was female, what percent of the population were of working age. We also know things like life expectancy, infant mortality, various demographics. It's an interesting data set. It varies Well, from 1961, I think I have data all the way through about 2009. That was the last year that they had available when I pulled the data, for about 170 countries. Now, if I have demographic information like that, the sort of questions I might ask are, first off, if I'm particularly interested, let's say, in life expectancy, how does life expectancy vary throughout the world? I could also ask, is life expectancy related to other demographic factors? And since I do have data over time, it's also interesting to ask, how has life expectancy changed in recent years? Now, the first graph I'm going to look at, which will be graph number 5 of my top 10, is a dynamic bubble chart. You've probably seen this graph before. It's one of my favorites because it's a very informative graph. What you see here for the year 1961 is a bubble for each of the countries in the World Bank dataset. The bubbles are plotted at positions such that the position along the y-axis represents average life expectancy in a particular country. The x-axis is fertility rate. That's the average number of of children per woman. How many children does an average woman have in a particular country? The color of the bubbles represents the infant mortality rate, blue being low and red being high. The size of the bubble is the percent of the population that live in rural areas. Now, what you see in 1961 is that there were basically two groups of countries. There were countries up here, mostly in Europe and North America, the more developed countries, where life expectancy was in the neighborhood of 70 years. Average number of children per woman was about 3. Infant mortality relatively low. And the rural population also relatively low. These bubbles are a lot smaller than most of the bubbles over here. In this group of countries, which was the rest of the world, you can see considerably shorter life expectancy. Life expectancies ranging anywhere from 30 years up to about 65 years. Average number of children per woman, somewhere between 6 and 8 children per woman. Definitely some higher levels of infant mortality. You see reds and oranges that you don't see in the other group. And by and large, the bubbles are larger because larger percentages of the population of those countries live in rural areas. Now, this is another statlet, the way we've implemented it in Statgraphics, so I can add some animation to it and watch how things have changed over time. So let me open up my World Bank demographics Statfolio. There we go. That's what the world looked like in 1961. I'm now going to let it change year by year, and you'll be able to watch how the world has changed. General pattern over time has been for all countries to move up toward the upper right. Life expectancies have grown pretty much everywhere around the world. The fertility rate has come down. Fewer children per woman in 2009, quite a bit less than it was in 1961 when we started. Thankfully, all the reds and oranges have disappeared as infant mortality has come down around the world. And you can also see in many cases the bubbles are getting smaller as less and less people live in rural areas. It's interesting to watch. You can also see a few outliers. I happen to know that this particular country here, in particular here, is Yemen. While the rest of the world was moving toward fewer and fewer children. This is Yemen here. For a while, the fertility rate in Yemen was getting higher and higher. But then eventually, toward the end, it moves in the same direction as all the other countries. Very interesting plot that you can see for the world demographics. Another interesting way to show changes in life expectancy is to do it on a map. Okay, we also have a dynamic map where we can plot for every country around the world the life expectancy using color codes. And I've coded my maps such that dark blue would be a life expectancy of 30 years, dark red a life expectancy of 90 years. You can see back in 1961, there were a lot of blues, particularly in Africa, and the highest life expectancies appear up here in Scandinavia. Well, let's let the years evolve now, and you'll see changes in color. Pretty much everywhere you see the blues disappearing, you see the light greens moving toward dark oranges as life expectancy increases around the world. Another very interesting way to look at one important aspect of the demographics of the world. Incidentally, I will be providing at the end of the webinar all of these data sets so that you can try these yourself, and you may find some other graphs that you think do a good job of showing the information in the data set. But for me, graph number 5 was a dynamic bubble chart. Graph number 6 was what I'll call a demographic gradient plot, where we show the distribution of a particular variable with a gradient of color. All right, now another data set I find quite interesting is data on seawater temperatures. There's a lot of discussion, obviously, these days about global warming and the impact it's having on climate around the world. Well, one very interesting index that NOAA, the Climate Prediction Center at NOAA, maintains is a measure of temperatures in the tropical Pacific. In particular, there is an index called ONI, the Oceanic Nino Index. Okay, and I have a data set that I got from NOAA showing what the Oceanic Nino Index, the ONI, was on a monthly basis going 825 months back into the past. Now, the ONI is an interesting index. It's an index of seawater temperatures, as I said, indexed such that 0 would represent an average temperature. A number above 0 would indicate seawater warmer than average, a negative seawater lower than average. And there's some rules about the ONI. If the ONI falls below minus 0.5, NOAA regards that as a La Nina. If it goes above 0.5, positive 0.5, it's an El Nino. Now, it's very interesting to go back historically and look at the occurrences of La Niñas and El Niños. They have a big impact on the weather, certainly in the United States. Now, the sorts of questions that one might ask of this particular data set are the following. First off, what does the cyclical pattern of La Niñas and El Niños look like? Okay. How long do such events usually last? And what type of period are we in currently? Now, to look at that, I'm going to nominate as graph 7 a time series baseline plot. A time series baseline plot takes a time series, monthly data, in this case, the ONI going all the way back to January of 1950, plots it with a horizontal line at the baseline, in this case 0, and upper and lower limits, in this case at 0.5 and minus 0.5. It also shades the areas above 0.5 and below minus 0.5. The reason we do that is that it makes a much more dramatic and interpretable presentation. For example, you can see in the last 65 years that there have been approximately 20 El Niños that have occurred. Somewhat fewer La Niñas. You can also see that the duration, though, of the La Niñas tends to be a little bigger on average than the El Niños. This particular peak, for example, is about 1, 2, 3, 4, 5, 6, 7, 8, 9, maybe 10 months, where this La Niña down here is considerably more than that. As far as the cyclical pattern is concerned, it's not a regular pattern. The length of time between the occurrences is somewhat irregular, particularly the occurrences of La Niñas. You can also see at the end of the data, and I think the last data point was centered at September of this year, it does appear that we are entering a period of an El Nino. It'll be, it's a little hard to tell how long that's going to last. Sometimes it doesn't last very long. Sometimes it lasts, as I said, up to about 10 months. So that's the time series baseline plot. And I think it's a very useful graph for looking at time series data, particularly if you have an upper and lower limit with a particular meaning. Okay. Now, another data set I'd like to look at is the price of Bitcoin. There are quite a few applications of time series and procedures in Statgraphics to look at time series. Some of my friends tell me I don't look enough at financial data. Have a lot of scientific data, not enough at financial data. So this is going to be my example of financial data. What we have in this particular data file, it's called Bitcoin Price New for those of you who want to look at it after the webinar, is daily information starting on January 1st of this year of the prices of Bitcoin. In fact, we know the closing price of Bitcoin on any given day. We know the opening price. We know the high, and we know the low. Okay. Now, the best way to look at that particular data Well, I'll show you in just a second. The questions I might like to ask, though, are first off, how has the price of Bitcoin changed over the year? Have there been periods with more volatility than others? And thirdly, what's likely to happen to the price over the next few weeks? Now, the graph I want to show you is a open high-low closed plot on which I've superimposed some forecasts. In Statgraphics, we create a plot called an OHLC plot, which plots on any given day a bar ranging from the high price during the trading session to the low price. You can see that on any given day, there have been days, particularly at the beginning of 2018, where the price fluctuated by several $1,000s on any given day. Then there have been periods in September and October where there was very little change. An open high-low closed plot consists of a bar on any given day, ranging from the high price to the low price. And incidentally, those bars are drawn green if the price went up during the day, and they're drawn in red if the price went down. Superimposed on top of those bars is a smoother. In this case, it happens to be an exponentially weighted moving average, in which I've chosen a smoothing parameter of 0.2. Above and below the smoother, you also see something called Bollinger Bands. What Bollinger Bands do is show you an estimate of the volatility of the prices at any particular point. Bollinger Bands are created by estimating the standard deviation using a moving average. We then basically take that moving average estimate of sigma and plot from the EWMA plus and minus, in this case, 2 times that estimated sigma. It's a measure of volatility, and you can see back in the beginning of the year, January, February, March, the bands were fairly far apart, an indication that the prices were quite volatile then. On the other hand, as you get over to September, October, November, you see the Bollinger Bands were very tight. Then, of course, came December, and there was, again, a dramatic drop in the price of Bitcoin. And you can see not only the moving average comes down, but the bands increase. Now, what I've done in Statgraphics is, in addition to the open, high, low, close plot, I've also put that data through the automatic forecasting procedure. The automatic forecasting procedure in Statgraphics fits a lot of different forecast models and picks the one that does the best job in forecasting observed behavior. And for the Bitcoin prices in 2018, the automatic forecasting procedure selected an ARIMA 1-2-1 model. And I actually fit that ARIMA 1-2-1 model to the logs of the prices. Because of the dramatic changes in the price, I thought it was best to fit the models to the logs. Now, when I first wrote this webinar was back on December 15th, and the price of Bitcoin was going down, 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 down. Well, over the last couple days, it's rallied and gone back up quite a bit. So this morning, I updated my forecast to see, taking all data through today, through the 19th of December what the forecast for Bitcoin would be. You can notice here that it's rallied somewhat. However, the forecasting model still sees a predominant downward trend in Bitcoin prices for the rest of the year, although the 95% forecast limits certainly say it could go either way. Slight tendency to go down. However, given the volatility in Bitcoin prices, the forecast model with 95% confidence really thinks it could go either way. An interesting plot, I thought, the open, high, low, close plot, and I used the stat gallery, incidentally, in Statgraphics to superimpose the forecasts from the automatic forecasting procedure on top of that open, high, low, close plot. Okay, so we'll make that graph number 8. Graph number 9 will be a graph that's good at illustrating my 7th data set. The 7th data set I'm going to look at today is fish counts in the Gulf of Maine. It turns out that every year they go out and at various locations in the Gulf of Maine count fish. I think they put out some nets and troll along for a while, pull in the nets and count the number of fish. I have a file called Gulf of Maine that shows from 1963 on how many fish were seen when they did that count in the Bay of Fundy, in Browns Bank, in the central Gulf of Maine, in the continental slope. I think 13 different areas in the Gulf of Maine. The questions you might like to ask of this particular data set, first off, it would be interesting to know how have fish counts changed throughout the years? Which years and which locations have had the highest counts? And also a third question might be whether there's a correlation between the counts observed at different locations. An excellent graph for doing that is a heat map. The heat map will be my graph number 9. What the graph shows you at one glance, actually, is for the 13 locations in the Gulf of Maine, what the fish counts were from 1963 through 2003. That's the span of time that those counts covered. There is a little rectangle drawn for every combination of location and year, which is color-coded so that dark blue represents a count of 0, dark red a count of 160. Well, you can see a number of things very quickly from this heat map. First off, you can see that there are 2 locations that are consistently high. We have the central Gulf of Maine here, and we have Georges Bank here, where the counts have consistently been above the other regions. You have certain areas like the Bay of Fundy where you almost never see any fish. Same thing with Browns Bank. You can also see that there have been certain periods, certain years, where the counts have been higher than average. In particular, from 1977 through 1982, you see very large counts both in Georges Bank and in the central Gulf of Maine. And during that same period, a couple other areas showed larger than normal counts for those locations. So there definitely does appear to be some correlation between what happens in one area and what happens in another. On the other hand, there are some years when one location is high but you don't really see that reflected anywhere else. A very nice graph, I think, the heat map for showing the distribution of a particular variable by category and time. Well, actually, it could be any two categories. I find it particularly effective if you look across time, but it could be any two categorical factors. Okay, that'll be graph number 9 of my top 10. For graph number 10, I've picked the last data set that I want to look at today, my 8th data set. This is a data set having to do with commercial airline flights in the United States. I have a data file. It's called 2008 flight data with almost 7 million rows. Most of the data sets we've seen up until this point have been a few hundred, maybe up to 1,000 rows. This particular data set is larger. It's up around 7 million rows, one for every commercial flight in the U.S. during 2008. Well, there's a lot of interest, obviously, these days in big data. It's becoming easier and easier to collect data, and the idea of having millions and millions of observations is something that we need to deal with these days. It is somewhat of a challenge to display things graphically, though, when you have millions of observations. The sorts of scatter plots that we might use with hundreds of observations become just big black blobs when you try to plot 7 million points, for example. However, we still have interesting things to ask, obviously, about large data sets. Of this flight data, for example, I might be interested in knowing what the distribution of departure delays is. Another interesting question, are arrival delays related to departure delays? What is the relationship between how late you arrive at your destination to how late you left, you departed? And then, of course, there's also the problem about how clean is your data. Well, I wanted to go over now back to Statgraphics and actually load up this particular data set for you. I have a data file. It's called 2008 flight data. There it is. It has, as I said, something in the area, well, actually it's slightly more than 7 million rows. Well, let's go ahead and do a regression. Let's select simple regression and ask it to fit arrival delay as a function of departure delay. We'll go ahead, we'll take a linear model, and what I'd like to see an analysis summary and a plot of the fitted data. Okay, there we go. There were actually about 6.8 million rows in the file that did not have missing data. There was some missing data there. You can see it did a regression. The R squared is about 86.7%. In terms of illustrating the fitted model, though, Statgraphics, whenever it encounters large data, typically more than 100,000 rows, will automatically switch from a scatter plot to a hexagon plot. And plot number 10 of my top 10 for 2018 will be this hexagon plot. Now, what's a hexagon plot? Well, what happens when you have lots and lots of observations where a typical scatter plot would be meaningless? A hexagon plot can be constructed by forming what's called a tessellation of the space, the XY space, with a grid of hexagons. Basically, there's a 50 by 50 grid of hexagonal regions that are formed. And then, rather than plotting each individual observation, we count the number of observations that fall within each hexagonal region. Now, if there's no more than 2 observations in a particular hexagonal region, the points will be plotted separately, as they would on a scatter plot. However, if you have 3 or more observations in a particular region, we color code the region according to how many observations are there. So where you see these dark blues, there are probably hundreds of thousands of observations in those particular regions. In this case, incidentally, the arrival delay is very strongly correlated with the departure delay. It's interesting to note, actually, the slope is slightly greater than 1. So it looks like people tend to lose maybe a little more time, particularly if they get delayed for some reason, weather or whatever it might be. Anyway, that is the fitted regression. You can see that most of the points lie close to the line. Yes, where the dark blues are. Quite a few points slightly above the line, not many below the line, definitely skewed to the upper side of the line. A hexagon plot, much, much more informative than a scatter plot of 7 million observations. Okay, so number 10 of my top 10 is the hexagon plot. Okay, for those of you who are interested in trying out these particular data sets, I will post them at www.statgraphics.com/webinars sometime this afternoon. We'll also have a recording of this webinar posted in case you'd like to listen to it again, or if you have friends you think might be interested in what we've done. Okay, now let me see if there have been any questions submitted. As usual, we have the ability, since we're using GoToWebinar, of of having you submit questions. I'm reading the questions here. All right. One question: how many data rows were there for the wind rose diagram? Okay, yes, the wind rose diagram back here showed the wind at Midway Airport on an hourly basis starting at the beginning of 2018. So I had data for 24 hours during the day for every day. I think it was up through December 15th. So about 300, well, actually it says right here what the sample size was. In the case of the monthly data, the sample size was 740. Okay, that was every hour, once an hour for every day of the month. Back here, the sample size was 348. That was once a day at a particular time for 348 days. So it's quite a bit of data that's being summarized in the wind rose. Okay. Someone asked if I could remind them of number 2 and number 6. Well, actually, let's do a quick summary. Graph number 1 was the violin plot. Graph number 2, the bivariate density plot. In 2 forms. It could be a surface plot or a contour plot. Graph number 3 was the population pyramid. Graph number 4 was the windrows. Graph number 5, the dynamic bubble chart. Graph number 6, the demographic gradient plot. Graph number 7, the time series baseline plot. Graph number 8, the open, high, low, close plot. Graph number 9, the heat map. And graph number 10, the hexagon plot. I'll add a list of those to my slides here before I post them on the website. All right, for number 10, can you create a hexagon plot for any scattergram, or is it just available for display of the regression? No. In Statgraphics, if you have more than 100,000 observations, wherever it would have done a scatter plot, it'll do a hexagon plot instead. So if it's an XY plot, it'll make it a hexagon plot. If it's showing residuals and there's more than 100,000 residuals, it switches to a hexagon plot. Any place that it would normally do a scatter plot, it will switch to a hexagon plot, because otherwise the plots tend to be unreadable. All right. Any other questions? That's all the questions I see that were submitted. As usual, I invite you to send me questions if they occur to you after we end the webinar. My email is Neil, N-E-I-L, @statgraphics.com. If you think I've missed some plots that you feel are quite useful as well, you're welcome to send those to me. Otherwise, I thank you for your attention, and have a great remainder of 2018.